Hi everybody, Jonathan here. In this video, I'll be giving you my take on section 6.3, which is about finding volumes of rotation using something called the shell method. So right now, we've got this area, which is the area enclosed by the function, by the curve y equals minus x times x minus 3, the vertical lines x equals 0.3 and x equals 3, and the x-axis. So if we rotate this about the y-axis, we will get a lovely looking solid, which I can demonstrate. And by moving this slider along, oops, you can see we get this lovely looking shape. So how can we find the volume of this shape? Now, in order to get the volume of that solid of revolution, we start with the area. And we're going to divide the x values, the interval of the x values over which we have the area, into n equal parts. And we'll use rectangles above those intervals to approximate the area, like so. Now, we're trying to get this whole shape. We're trying to get the volume of that shape. In order to approximate the solid, we're going to rotate each of these rectangles around the y-axis. Every time you rotate one of these rectangles, you get a cylinder. Now here's the cylinder we're going to get when we rotate one of those rectangles. So there we are with this lovely cylinder. And there's a nice formula for the volumes of all those cylinders. And we can do it not just with one of the rectangles, but we can do it with all of them. So here are what things look like when I rotate every single rectangle around. I've only rotated halfway around, but this is sort of a nice cutaway view, which shows how we're approximating the overall shape with all of these cylinders. Now, just to demonstrate it, there's the entire solid. And as you can see, the entire solid it's a halfway decent approximation with all these cylinders. Now, remember, this all started by dividing the interval over which we have area into subintervals. Right now, this is for 4 subintervals. If I increase the number of subintervals, we'll get a better and better approximation. The volume of all the shells, the solid created by all the shells, will get closer and closer to the actual solid we care about, as you can see by turning that on and off. Now we need to get a formula for the volume of one of these shells. Each shell is simply a hollowed out cylinder. The formula for the volume of a hollowed out cylinder is 2 pi times the average radius of the inner cylinder, which has been hollowed out, and the outer cylinder, times the height times the width. So for this cylinder, the average radius is going to be what we call xi bar. So xi this is the average value of the left endpoint and the right endpoint of the ith interval. And then the height is then f of xi bar, which is just the distance up to the graph when we project back into 2 dimensions. And then the width is just our delta x. It's just the width of our rectangle that we started with. So now that we've got the volume of one of these shells, we know that our overall volume for the solid that we really care about is going to approximately be the sum of the volume of all the shells. So we just take up those volumes of all those shells and add them up, and we'll have our approximation. And by taking a limit as n goes to infinity, so as I increase n here, we get a better and better approximation. And then by taking the limit as n goes to infinity of that approximation, we'll wind up with the exact volume of the solid of revolution we care about. And that's going to turn out to be the integral from a to b of 2 pi x f of x dx. Now you are all welcome to go ahead and play with this app yourselves. I'll put a link to it on the under the course materials section in Blackboard. So this was for a function that I thought the graph would make a nice looking solid, but you could always change it to everybody's old favorite x squared. And then just for fun, we can rotate that around and see what kind of shape we'll get. So, oops, let's not show the one shell. And here we're getting this kind of solid cylinder with a hollowed out parabola in the middle of it. Or you can do all your other fun shapes. Maybe it would be fun to do like a sine of x. And here's the shape we'd get for a sine of x. Or maybe you'd like to see something like e to the x. It's not letting me do e to the x. I'm not sure why. Let's just do 2 to the x. I guess it doesn't know about e. It's stupid. So here's the shape we'd get for 2 to the x, and so on and so on. So feel free to have fun with it. You can change the bounds of integration if you want, and see what cool shapes you can get.